To have my friend, Dr. Alexandra Pope, Alex Pope, visiting. Let's see, I first learned about your work when she was still a graduate student, writing works using scuba when you were doing your dissertation up in Canada. Before, wait, I should have asked you before. Did you take directly the Spitzer Fellows following graduation?
Yes.
So then I knew her better. We were both Spitzer Fellows in Tucson, Arizona.
Yeah.
She's working across the street at the National Observatory. And before taking a faculty job at the University of Massachusetts, where she is today. And today she'll be telling us some of the work she's been doing. She's still working on very long wavelength astronomy and astrophysics, and she'll be telling us about some of the work she's been doing recently. So thanks, Alex.
All right, great. Thank you very much, Casey. And thank you for having me here today. I'm sure most speakers that come in the winter from the north say appreciate the weather, but I do appreciate the weather, especially all the storms we've been having up in the northeast. I come from UMass Amherst. Okay, so I'm going to be talking about dust-obscured activity in high redshift galaxies, and by activity I mean the growth of stars and the growth of black holes within galaxies. And by high redshift I mean usually from about redshifts 1 to 4, so half the age of the universe back to a few billion years beyond that. Not high redshift at 7, 8, 9, 10, 11 that we're talking about in other studies. And I'm going to be talking about observational programs that have been done to address these topics. In the past sort of decade, our understanding of these processes of star formation and black hole growth have grown considerably, and mainly because we've had access to telescopes that have revealed the hidden side of galaxy evolution and formation that is obscured by dust. And so the Spitzer Space Telescope is the first very high resolution near-infrared, mid-infrared observations. Herschel Space Telescope came along 5 or 6, 7 years after that, accessing the peak of the far-infrared dust distribution. And then the future in this field is really good right now. We've got ALMA, the Atacama Large Millimeter Array, which is going through its early phase and already is much more powerful than anything we've had before. And we've got a bunch of large single-dish sub-millimeter, millimillimeter telescopes coming online. So that's what I'm going to go through today. But first, let's start with a motivation. I'm just going to move over to this side so room. Okay, so to motivate why we want to study galaxies behind dust. Most of galaxy formation and evolution occurs behind dust, and I'm going to show you that in a couple of slides here. And the most fundamental piece of evidence for this is the infrared background and the optical background. So this is a plot of the total power in the universe from everything coming towards us as a function of wavelength here on the bottom. Oh, you were right, this is dying. She gave me an extra one. Okay. So here we've got optical wavelengths. Here we've got infrared wavelengths, and of course this is the cosmic microwave background, which has much more power in it. But everything we know about galaxy formation and evolution is coming out in these two backgrounds here. So there's two things to note on this plot. First, these numbers give you the integrated amount of power in the optical and the infrared wavelengths, and you can see that these numbers are almost the same, which means that we're getting just as much power from optical photons as we are from infrared photons arriving to us from galaxies integrated over all redshifts. The second thing to note is if you look around in the local universe and you count the amount of light that's coming from optical photons versus infrared photons from star formation and black hole growth, you see way more activity that's unobscured. You don't see as much obscured activity in the local universe. So in order to make these two things equal, integrated over the whole universe, these processes that are absorbed by dust and re-radiated in the infrared have to become much more important as you move to higher redshifts. Okay, and that's what we see. So these are plots from Buens et al. So this is from a study of galaxies selected at UV wavelengths, where they use the UV slope to make corrections for how much dust is in to account for the total amount of star formation rate density, so amount of star formation per volume, as a function of redshift here. And the blue curve here is what they're actually observing, so those are the UV measurements they're making, and then they make a correction upwards to account for the light from those new stars forming that has been absorbed by dust and re-radiated in the infrared. So you can see that most of the emission is coming out as actually absorbed by dust and re-radiated, and it's just these dust corrections. But we aren't directly detecting this emission here in these studies. You can also see that from this plot on the right, which is just the flat fraction of the flux density as a function of redshift coming from different wavelengths or populations. So the direct UV light, so this starts at redshift 2, because Boone's is more concerned with these galaxies out here. But if we just look between 2 to 3 here, you can see that the direct starlight in the UV is a very small fraction. 25% is actually coming out in the UV. Most of it's coming out and reprocessed in the mid-infrared and far-infrared in these UV-selected galaxies. And then a small fraction is coming out in these very extreme ultraluminous infrared galaxies that I'll introduce in a minute. Now, of course, as you go to the very distant universe, there's less dust because you need to build up dust in the universe. And so I'm mainly going to talk about this period here from about redshifts 1 to 4. Okay, so dust-obscured activity dominates the buildup of stellar mass in black holes and galaxies. And this occurs mainly at redshifts 1 to 3. So the plot on the right here shows the stellar mass density, so the buildup of stars in the universe as a function of redshift. This is sort of the classic paper Mark Dickinson and Casey worked on back in 2003. They were the first ones to do this. And this shows that half the stars in the present-day universe were formed between redshifts 1 and 3. Okay, so there's a large baseline in redshift, but between 1 and 3, you're forming half the stars in the universe. And you can see this from this previous plot. You've got this peak in the star formation rate density. You're forming way more stars per volume at these redshifts. The plot on the right here shows that you also see the same peak between redshifts 1 to 3 for the growth of black holes. And so all the colored points here are just meant to show star formation rate density, so you can just see that there's a peak. That's the main thing I want you to see here. And then the black curves with the gray are showing the evolution of the quasar population. So these are black holes that are rapidly accreting material and growing very, very fast. And you can see that the space density of quasars, the peak period corresponds to the peak period of star formation galaxies. We also have further evidence that the stellar mass and black holes are growing together from the locally observed M-sigma relationship or Megorian relationship, which shows that the bulge of galaxies, the mass of the bulge is correlated with the mass of the black hole. And so we know that these things are growing together, and we can see them growing together during this peak period. Okay, and then at this epoch of redshifts 1 to 3, where you have most of the star formation obscured by dust, and you have half the stars in the universe forming, it's occurring in the more infrared luminous galaxies. So I'm going to introduce an acronym here. I'm going to try and be acronym light in this talk, but I can't get away with this one. So ultraluminous infrared galaxy is ULIRG, and this is just a very dusty galaxy. So it's something that emits the majority of its light in the infrared, and barely any of the optical and UV photons are escaping from this galaxy. And then the luminous infrared galaxy is slightly less. So the numbers to remember: the Milky Way is forming stars at 1 solar mass per year, LIRGs are about 10 solar masses per year, and ULIRGs are hundreds to thousands of solar masses per year. So it gives you a scale of these systems. And so detailed studies that have broken down the sort of the demographics of galaxy populations that are dominating during this epoch show how, so this is the total, so this is showing the total star formation rate density ramping up between redshift 0 and 2.5. So zoom in on this portion here. If you look at normal galaxies, which are things less than tens of solar masses per year, they sort of have a pretty gradual increase and then flatten out. And then it's these galaxies forming tens of solar masses per year and hundreds of solar masses per year. They have much steeper evolution and they ramp up. So they become more important in the high redshift universe than they are in the local universe. And more of the stars are being formed in these systems than they are in the local universe. Okay, so this is why we're going to study galaxies at this epoch. So we've learned a lot already about sort of where to look in the universe, what observations we need to look at, but there's still some very important outstanding questions. So here I highlight 2 important questions that are sort of big picture questions, and then I break them down into 2 sort of more addressable questions with current observations. So how is the star formation linked to the black hole growth? This is a huge question. People are studying it at a range of redshifts. Something that we can try and address is, can we even separate the emission from each of these processes in our observations during this peak epoch where we know both things are going on? So that's the first one I'm going to try and address. And the second one is, are the mechanisms for triggering and fueling star formation during this peak period different from what's happening in the local universe? And so we know we have this peak period here. How do we have all this enhanced star formation activity? Do we have additional mechanisms that become important? This, again, is a very big question. A lot of people are working on this. The debates of mergers versus cold flows have been going for 5 years now. So I'm going to try and address this by looking at how do the interstellar medium conditions, and by that I mean the properties of the dust and the gas, differ during this peak period than in local galaxies. So I'm going to look at detailed properties of these high redshift systems and compare them to what we see in local systems. Okay. So back to these ultraluminous infrared galaxies. For those of you who haven't heard a lot about them, It's simply a definition in infrared luminosity. So it's systems that are greater than 10 to the 12 solar luminosities, which is about 100 to 200 solar masses per year, depending on which IMF you use. In the local universe, we have some of these systems, but they're rare. They're very rare. And it turns out, and we can get complete samples because they're in the local universe. So we can look around and we can identify all of these. We aren't biased in terms of how we're selecting them. We know what's happening with their AGN, their dust temperatures. And we see that most of them are major mergers. In fact, almost 100% of these ULIRGs are major mergers, and a large fraction of the lower luminosity galaxies are major mergers. Okay, so what do we do as we move to higher redshift? We want to select comparable objects. And we've had to rely on all of these acronym techniques, which I'm not going to go over all of them, but they're different techniques that we've utilized to select things that we think are bright in the infrared. So one that I'll highlight here is SMG, which is submillimeter galaxy. So this is selecting something that has a lot of submillimeter emission, because at redshift 2, that submillimeter is shifted up to the peak of where the infrared light comes out. And so that's been a very effective way. Spitzer allowed us to make up a bunch of new acronyms for selecting things. We can also use optical colors to select things that we think are dusty, or UV colors. But the point here is that all of these selection techniques are different, and you could draw some very complicated Venn diagram of the overlapping populations, and there's many papers that have tried to quantify this. And the bottom line is not any one of these techniques picks out everything that's bright in the infrared. And you really do need to sort of determine what your selection biases are. So the point of this slide is to show you that it's hard to even just get a sample of these things at high redshift that you know is complete to be able to draw general conclusions about the population. Now, I thought when I was doing my PhD and I heard about Herschel, which probes right at the peak, we're going to be done with this when we get Herschel. We're not going to call these things any of these. We're just going to call them ULIRGs at redshift 2. But now we've got all these new acronyms with Herschel because it turns out the confusion limit is still fairly high, and so we're not getting down to typical star-forming galaxies. Okay. Nevertheless, I will discuss samples that we've selected from a number of these techniques and what we've learned from them. Okay, so the spectral energy distribution is perhaps one of the most useful tools that we have to pull out intrinsic physical properties of galaxies. And what it is just the luminosity density as a function of wavelengths or frequency, depending on how you like to do it. And this one's showing the optical over here and the infrared over here. So this is what an ultraluminous infrared galaxy looks like. Most of the light is coming out from this infrared bump, which is usually characterized by a couple of black bodies or a gray body, and then not very much light is coming out from the opticals here. So this is the direct light from stars, young stars down here and the old stellar population up here, and then most of this light from these stars is absorbed by dust and re-radiated to create this big peak here over the infrared. So, now we have a very good sampling of this peak. Prior to Herschel and Spitzer, it was pretty bare and we had to rely on single photometric bands. But we're now in a position where we combine all these data, model them properly, and pull out physical parameters. So I'm going to talk about two sort of regimes of the SED today and what we can learn. And so at the far infrared wavelengths here, we're probing the emission from large dust grains. And I'm going to talk about what we can learn from the imaging here from Herschel. But I'm also going to talk about what we can do in the mid-infrared here. And specifically, Spitzer had the infrared spectrograph, which provided mid-infrared spectroscopy at these wavelengths, which is, as I'll show you, extremely sensitive to whether or not you have star formation or black hole dominating the emission in these galaxies. So I'm going to talk a little bit about how we integrated in those diagnostics from the small dust grains as well. Okay, so let's start with the mid-infrared stuff. So mid-infrared spectroscopy was first sort of established as a way to separate the processes of star formation from AGN activity with isospectra, and this was only done for local systems because ISO wasn't sensitive enough to really probe out to higher redshifts. But this just gives you an example of what these spectra look like. So they usually run from about 5 to 12 microns in the rest frame, and here if you look at the spectrum of starbursts, galaxies that we know are starbursts, versus galaxies that we know are AGN, you can see that they're different just from comparing these two plots. So the starbursts have these features, which is these polycyclic aromatic hydrocarbon features, which occur in PDRs next to star-forming regions. And AGN just sort of have sort of a power law distribution, which happens from a combination of a bunch of warm black body dust distributions combined together. And so here is sort of just, you're just looking at the spectra. Here they've actually done a diagnostics where they've taken the ratio of one of these features to the continuum as an indicator of how much AGN activity and how much star formation. And so you can see that the starbursts lie up here with high values of POF, continuum, and as you go to systems that are more AGN dominated, that decreases, as you might expect to get to the pure power law. So this was very promising, and when the Spitzer infrared spectrograph came around, we were able to push this to higher redshift. Oh, sorry, before I get to that slide, I just wanted to show you sort of theoretically why we expect these things to actually separate in the way that they do. So this is just an empirical result here, and here's what's actually happening. So if you look at a star-forming region like Orion, where you have an H2 region and then a border with a molecular cloud and a PBR in between, you can map out where the PA emission is and where the molecular hydrogen emission is and where the CO emission is. So here's the H2 region over here, and here's the molecular cloud. And you can see sort of that the PA emission is coming from very close to where the H2 regions are and should be a very good indicator of current star formation activity in galaxies. And so if you have a lot of star formation, you should see a lot of PA emission. If you have an AGN, what happens is one of two things. Either the AGN is powerful enough to destroy the molecules, the PA molecules, because they're fairly sensitive, or you can just have the emission from the warm dust become so overwhelming that you no longer see the emission from PAs. And we can't really rule out one of those when we just have unresolved observations. But either way, if you're seeing the smooth continuum, you know that most of the photons coming out in that regime are coming from the AGN. And then this is just a little schematic of the H2 region showing where the different species come out. Okay, so let's move now to higher redshift. So this is just a paper, one of the earlier papers from the IRS team showing how they were able to do this at higher redshift. So here are a bunch of sources which they classified as starbursts. Now you're seeing these spectra are looking a little more low signal to noise, right? We're pushing these to the limit. But you can see the difference. Features in these ones, no features in these ones. Sometimes these ones have this little dip here, which is absorption from silicate. It's not completely understood what the silicate is coming from, but it seems to correlate with more obscured AGN. And so I'll maybe mention that a bit later. Okay, so what I worked on is the Redshift 2 submillimeter galaxies, and we had a program to look at the infrared spectra of these Redshift 2 submillimeter galaxies, and the goal of it to see, do these submillimeter galaxies, which have star formation rates of 100 to 1,000 solar masses per year, are those really star formation rates for these galaxies, or is some fraction of that emission that we're seeing at these submillimeter wavelengths just emission from the black hole that's contributing? And so if the black hole is contributing, you'd expect a power law here. If it's mostly star formation, you'd expect to see features. This is our composite spectrum from that study, and you can clearly see these bright features here. And when you quantify this, you find that the AGN component down here only accounts for 30% of the mid-infrared light. And when you do the K corrections to longer wavelengths, it ends up contributing only 10% to the total infrared luminosity. So these systems really do have star formation rates at the level of 1,000 solar masses per year. That's pretty well understood now, but back, when submillimeter galaxies were first introduced, people said there's no way you can create that. The models still have a tough time getting up to those kinds of luminosities. Okay, but the point I want to make here is that this is not what local systems of similar luminosities look like. If you look at a local ULERM that's forming stars at 100 to 1,000 solar masses per year, it's going to have mostly a smooth continuum. Most local ULERMs up at that luminosity level are dominated by the AGN emission. This spectrum looks much more like M82, which just is a lower luminosity starburst galaxy. Another way to see that is to look at a plot like this, which plots the luminosity of the PA emission as a function of the infrared luminosity. These are the submillimeter galaxies up here at redshift of 2. These are local starburst galaxies in blue. These are a small sample of local ULERMs that we had available that are similar luminosity to these guys. If you fit a function to just the blue points, the red points lie in an extrapolation of them. So they're scaled up local starburst galaxies, which means that they may not follow similar properties to the local ULERMs in terms of the triggering mechanisms or the other interstellar medium conditions.
I'm just trying to remember myself. There's a lot of scatter.
Yes, there's quite a lot. Well, there's a lot of scatter in the starbursts
right,
too.
I was going to ask, do you think the scatter extrapolates or if it's bigger at higher redshift?
That's an excellent question, and something that I was hoping to address more with the larger samples that we're looking at.
Yeah.
We should talk in detail about it more later, but there's various issues with, there's various other things that the PAs are sensitive to, such as the ionization and various other things. So it's possible that something that's, with this small sample, we can't tell if the scatter is more for these ones as these ones.
Right.
But it is something definitely that would be interesting to look into if you want to calibrate it as a star formation rate.
Right. Why would the polyluminosity be extremely sensitive metals? After all, you're stringing
Right.
together 6 or more metals. Each one is down by a factor of 2.
Right.
you could easily have a factor of 10 difference in
Right.
luminosity and what other cooling is going on in the region.
Right.
As a function of this, how do you put any sort of limit on it?
Right, so we don't have metallicity measurements for any of these high redshift systems, but for, you know, a few lensed objects that you've been able to get enough lines to put metallicities, they seem like they sort of have typical regular solar metallicities, same thing as these starbursts. So we don't think that we have, and these are very massive galaxies, so they will be fairly metal rich. So we don't have much of a metallicity factor within these very bright massive samples. But I agree that once you go down to lower masses, metallicity is going to play a huge role. And there's definitely evidence in local dwarf galaxies from Spitzer studies that have shown deficiencies in PA emission for those systems.
I mean, maybe this is a side topic. It almost seems like it's not a continuum, it's more of a step function. Like once you hit some metallicity threshold, then the PA seems
Right,
more
the
of the
dwarfs
same
are
ratio
just down.
to the dust that's doing the thermal, the radiation, but that was not good grammar.
Right, it's not just pure metallicity, this is cooling rates and all sorts of other things.
Absolutely, but just empirically, when you look at PA luminosity ratios relative to, you know, H alpha or something like that, there's a threshold. Does that mean I'm just thinking about like?
Yeah, the stuff that people have done locally in the SING samples of local galaxies, right, exactly, yeah. So there's definitely tons of other things that are going to affect, you know, how the PAs are behaving in these situations. Okay, did I answer? Yeah, okay, we can talk more about it after. Okay, so the point here then is that these submillimeter galaxies look weird, but I showed you initially that these are just one part of galaxies that are luminous in the infrared, and so maybe it's just this one, you know, there's a huge scatter in here and we're just missing all these other galaxies on this plot. And so what we really do is want to, for any of these properties that we're trying to constrain, is take census of all these galaxies that are right in the infrared. So what we did then was we took, the IRS only lasted for 5 years, unfortunately, on Spitzer. It was extremely powerful. I think it became heavily oversubscribed in the last couple of years once we figured out what we could do with it. But then that was it. And so what we did with our group was we went back and we took all of the sources in the literature that anyone had taken for any reason, and we reduced any serendipitous sources that also lay in the fairly large slits that they had, to create this database of 150 sources from redshifts 0.5 to 3 that had mid-infrared spectroscopy, and we focused in the goods fields because those are fields that have the other very deep ancillary data that you need to do this kind of work. So 150 sources doesn't sound like a lot, but this mid-infrared spectroscopy is an extremely valuable piece of data. So this includes galaxies selected in all these different ways from this diagram here. So they're not necessarily weighted the same in terms of their populations, but they're all covered in terms of their properties. And we verified that they span the full range of mid-infrared and far-infrared colors that we see in all these large Herschel selected samples. So they should at least have sources covering all the parameter space. One of the other things that is an issue when you're reducing these very faint data and trying to measure these lines is the technique that you use to define the continuum and measure the line strength. So we reduced all of the data in the exact same way, measured all the lines in the same way, and measured the lines of the local galaxies that we were comparing to in the same way as well. So we did a spectral decomposition similar to what I showed on this plot, where you fit a model that includes the pHs, that's sort of your starburst model, and then a continuum with extinction for the AGN model. And we did that for all of the sources. And out of that, we get an AGN fraction, which is the fraction of the mid-infrared light that's coming from the AGN portion. We get luminosities for the PAs, we get luminosities at 8 microns from integrating on. So this is showing the redshift distribution of our sample. Don't worry about the different colors here, just look at the overall distribution. So this is basically a selection effect because it depends on which sources were chosen by various people. So this is not telling you exactly where all these sources lie, but this dip here is real because these sources are selected mainly at 24 microns, and at 24 microns the filter moves into where you have this silicate absorption in between the PA features. And so you do actually have, in a 24 micron survey, a deficit of sources there. It doesn't mean they're not there, those luminosities.
It's a narrowband survey.
Sorry? Exactly, right, yeah. And then this is just showing the 8 micron luminosity as a function of redshift to show that our sources that we define as AGN versus star formations of the AGN sources are the red ones and the starburst dominated ones are the blue ones, are kind of well mixed within this parameter space. Okay, so we can do this spectral decomposition. So here's an example on the left of a source that we would define as a starburst dominated source. It comes out as 5% AGN. And the one on the right is AGN dominated. You can see that the blue curve here is dominating the fit. The blue is the AGN component, green is star formation, and red is total. So this is just to emphasize, so we did this for all of the sources in our sample. And then within the AGN, we noticed that some of them sort of had this smooth continuum with no silicate absorption, and some of them had this very big bite taken out of them from the silicate absorption. And so we classified those separately so that we could study them differently, because the silicate absorption is something that's not well understood, and we wanted to try and tease that out. Okay, so when we did this for all of these sources, we in order to make progress, we split the sample into 4 different categories. So we separated the sources into ones that were dominated by star formation, like this, and dominated by AGN, and then we had enough of them that we split them by redshift. So we have a source of sources less than redshift 1.5 and greater than redshift 1.5. So we call it our redshift 1 sample and a redshift 2 sample. And then the AGN, we split them into ones that show prominent silicate absorption versus the ones that don't. Okay, so these are the 4 categories of sources that we're going to look at. About 3/4 fall in this sample and 1/4 falls in that sample. But that's purely a selection of the flux limit that you're looking at. And so if you break this down as a function of 24 micron flux and you look at the fraction of sources greater than that flux that are classified either by star formation, which is the gray, or AGN, which is the black, you see that at these mid-infrared wavelengths, if you have a fairly bright flux survey, which sort of the FLS team, for those of you who are familiar, you're going to get the majority of your sources are going to be dominated by AGN at these very bright mid-infrared fluxes. Doesn't necessarily correspond to far infrared. But as you move down to these deep depths, which is what we had in the goods fields, most of your sources are dominated by star formation. Okay? Oops. So I'll just highlight the outstanding questions again. So can we separate the emission from each of these in our observation? So I've shown that in the mid-infrared with the spectra, you can easily, but with a lot of work, you can separate the two and quantify them. But that's only the mid-infrared, and the infrared covers the whole range all the way out to about 1,000 microns. So really what you want to see is what is the impact on the whole dust? How much of the whole infrared light is coming out from star formation versus AGN? And so to do that, we got data from the Spitzer Space Observatory. So this was the Goods Herschel Key program that obtained the deepest far infrared observations, 5 wave bands over the peak of the distribution. This little plot here is one from our proposal that I really like still, that shows how you improve your measurement of the infrared luminosity as a function of redshift. This black is what you would have in terms of your error on LIR in DEX. If you only had a single 24 micron point, and then as you add 100 microns and 1 millimeter, you can tighten these up considerably. And so this is black is what we had to deal with before Herschel, and with Herschel we can now do things much more accurately. Okay, so here's some examples of how we've folded in now the far infrared data with the mid-infrared data. So on the left, I show a galaxy that was dominated by AGN as classified in the mid-infrared. So you can see the mid-infrared spectrum here. And on the right is star formation dominated in the mid-infrared. So you can see the spectrum here, you can see the features. And then we've combined it with the photometry that we have from Herschel, which span over the peak here. And then we investigated various ways to model this. Now, prior to Herschel, people would often just model the infrared with a single dust distribution, single black body, and say this is sort of an average temperature. And this is what we tried initially, and we found that it fit terribly. Now, we don't expect a galaxy to contain dust at 1 temperature. We also don't expect a galaxy to contain dust at 2 temperatures. But it turns out that a model that includes 2 temperature components is a much better fit to the data. And you can kind of think of this in terms of, if you're thinking of a star-forming galaxy, you have the dust around sort of the star-forming regions, the H2 regions, that's heated to a higher temperature, and then you have all the dust that's distributed throughout the galaxy that's at sort of a more cooler temperature. In the AGN sources, you could think of, if you've got the cooler dust that's coming from the host galaxy, and then the warmer dust could be the dust that's heated right around the AGN. So this is sort of the idea that we went into this thinking. Our goal was, can we find some sort of metric to separate the AGN and the star-forming dominated systems and quantify some difference? And this 2 dust temperature model seemed to work well. So here I'm showing the cool dust temperature in blue and the warm dust temperature in red. So unfortunately, not all of our sources have, this many data points, not all 150 sources, so we couldn't do this individually, but we could do this in sort of an average sense. And so we took those 4 categories, star-forming galaxies of redshift 1, star-forming galaxies of redshift 2, AGN with silicate and AGN without silicate. We combined all their spectral data, we combined all their photometry at all wavelengths, and made these composite SEPs and normalized them in the spectra here. So here's the star-forming galaxies up top, here's the AGN down here. You can see all the data that go into it, and then we fit all of them with these 2 temperature component models in the far infrared. And then we can start pulling out some of the data. So are some of the parameters that we fit to it. So the cold dust temperature and the warm dust temperature and the normalizations for each were both free parameters in these fits. And you can see that the cold dust temperature is always around 30 Kelvin, regardless of whether or not you're looking at an AGN or a star-forming galaxy. Whereas the warm dust component came out at something like 60 Kelvin, which is consistent with what we see for H2 regions around local star-forming galaxies. Whereas it's warmer, it's about 100 Kelvin for the AGN systems. Now, I'll point out here that ideally for these AGN, if we're thinking of a host galaxy that's just like this, with an AGN embedded in the center, you really are going to have a 30K, 60K, and 100K type system, but we didn't have the data to fit sort of a 3-temperature component model there. So we naively assume that this 30K distribution in both is definitely coming from star formation heated from the host galaxy. And for the star-forming galaxy, since there's no evidence of any AGN in the mid-infrared, the 60K component is also, for the AGN sources, this warmer component is most likely, most of it's coming from the AGN. Okay? So we can quantify that a little bit more. What we've done is we've determined an effective dust temperature, which is taking these individual components and luminosity weighting them depending on which one's more dominant. You can see here that this warm component is lower in the silicate than it is over here in the feature list, so that's going to be reflected in the effective temperatures. And you can see here that the effective temperature is very consistent for the star-forming galaxies, 37, 40K, whereas for the AGN it's much higher at about 58 to 65K. So we are measuring a genuine difference in the dust temperatures in these systems, which we've determined are either heated by star formation or AGN, and we've measured the impact of that on the far infrared.
Why don't they play devil's advocate in the lower left? The lower component goes to almost no data points.
And the lower, which one?
Lower left.
This one?
No, lower left.
Sorry.
58K, the blue dotted line, at least from back here, most of they're black dots that are way
Yeah.
that. And then right above, and then there are lots of black dots that are higher than that. So.
Yeah, no, you're right. So this is a combination of fitting to sort of the spectrum that's here and then the data points and the data points that are here. So I agree that this is not a perfect fit, and I think a lot of that comes from the fact that this is a composite thing. So we're combining a bunch of sources, there's issues with normalizations, and there is going to be some scatter. We did do, Monte Carlo realizations to quantify the errors and the uncertainties in all of these fits, and so so we're hoping that any sort of outliers or we've sort of included in that. But no, that's a very good point. So I mean, if you would argue then that the silicate would come down a little bit, this would get
It actually reinforces your state.
Right. Yeah. Exactly. Yeah.
I mean, if you compare to this physically, if you think about a silicate AGN,
yeah.
I mean, basically it just has a single 9.6 micron absorption
right.
feature. And naively, if I say, well, that's the torus of the AGN, so you're trying to
right.
prove that in some way.
Yeah. So that's a big thing of debate right now, actually, whether or not the silicate in the AGN is coming from the torus or the host galaxy.
Right,
this paper's going both ways, but that's sort of the traditional look that people have.
Right. So, I mean, I guess that's one way to actually interpret this plot, because if I look at it and said, well, what's different about the two?
Right.
One's just that presence. I guess if you're looking
right.
at the galaxy that's edge on, so you're looking through the silicates through the plane of the galaxy, then it could explain that because you're saying there's more.
So you see more of the host galaxy, and more of the AGN is being obscured by the torus along those lines as well. Exactly. So, yeah. So that's definitely something. I don't think I'm going to talk too much about the silicate AGN, but if you correlate it with other multi-wavelength indicators, if these are actually more luminous in the infrared than these sources, but these are not detected in the X-rays and these ones are. And if you determine the X-ray absorptions, a lot of these are potential Compton pair sources, whereas these ones are not.
But that goes along with what you were saying, that those are more detected in the X-rays. So
right. Exactly, which you would expect if you're not looking
funny composite thing.
Yeah, exactly. So we're actually looking into this issue more now. So this is the 150 sources from goods. Lately, my student Alison Kirkpatrick, who wrote the paper on this analysis, has taken now IRS spectra from all these other samples as well, including the FLS stuff, where they're much brighter, which means they have way more AGN. So we're trying to look at this very thing of how the AGN is turning on a little bit more. And she's finding some interesting correlations actually with what's happening down here in the near infrared as well, using the color. So that's sort of something to keep an eye out for. Okay, so the other thing then, an important thing to quantify is how much of the total infrared luminosity is coming from the cold component versus the warm component, particularly for these AGN sources where the warm component is most likely heated by the by the AGN. Now, people are often taking samples of AGN and studying them with Herschel and saying, oh, I'm at very, very far infrared wavelengths, so it's fine because that's all dominated by star formation. And that's not actually true. If you look at the featureless AGN here, if you look at the ratio of the cold dust to the total infrared luminosity, that's just 20%. So that would mean that if you use the submillimeter data points to derive a star formation rate for these galaxies, you would be off by a factor of 5. So that's too high, exactly, a factor of 5 too high, because you're not accounting for the emission that's coming through from the AGN in these systems. For the star-forming galaxies, you've got roughly 50-50, and so that might be the balance between what's coming from things closer to the PDRs and further away. And for the silicate AGN, you've also got more of a 50-50 split. So this looks similar to the star-forming galaxies in that, but remember that this is at 100 Kelvin instead of 60 Kelvin, so there are differences there.
So,
yes?
So when you say LIR here, you mean that's total volumetric?
8 to 1,000 microns, yeah.
8 to 1,000, okay. So, but if you're getting a star, if you're looking at the flux at, say, 500 microns, then it really should be dominated by the star formation. Is that right?
Right, if you were using the right model. I mean, if you were to, it would depend how you're doing this, because people will often just, take a measurement here and then take, whatever SED, right? I mean, I would say prior to sort of doing this type of work, people didn't have an idea on how these SEDs really changed as a function of these properties in galaxies. So you're right. Down here, if you look, most of it's the green curve, right? You got to get all the way down to maybe 100 microns before the blue curve starts being more dominated. So yeah, you just have a longer point. Most of the emission at that wavelength, but it's extrapolating to LIR. That's the problem. That's the problem. Yeah. Okay. Okay, so now looking for evolution. So within our sample of redshift, the reason why we split this into redshifts 1 and redshifts 2 is because we wanted to look for evolution as a function of redshift. And as I'll get to in a second, there's a lot of evolution between redshift 0 and high redshift. But between redshifts 1 and redshifts 2, these are our two composites, including all the error bars. They're virtually indistinguishable. The slight difference you see here is just the known evolution and specific star formation rates in galaxies between these two redshifts. So we don't see a lot of evolution between redshifts 1 to 2, but between redshift 0 and high redshift there is a lot. Now this is perhaps not the most inclusive plot to show this, but it's just a nice example. ARC-220 and NGC-6240 are two sort of prototypical local ULERGs that are often used to interpret high redshift galaxies. The pink is our composite, the black is all the data underneath it, and the blue and the orange are the other local ULERGs. And you can see that the high redshift galaxies always have less of this sort of warm dust here than the high redshift systems, or the other way around, the high redshift systems have much more cold dust relative to the warm dust than the local systems. Okay, so this is not completely new from this study. A number of people have found this together before. In fact, back in 2006, we looked at the submillimeter galaxies, and this was the first thing we saw for them. A number of studies with Spitzer also found it. So it seems like galaxies at higher redshifts have cooler dust temperatures, which could mean something different in terms of the distribution of the dust. It's more extended, and I'll get to that more in a second here. Okay. So, high redshift ULERGs look different from local ULERGs, both in the mid-infrared spectrum and in their dust distributions now in the far infrared. So could this mean different triggering and fueling mechanisms at high redshift? So there's this debate of mergers versus continuous accretion. Gas accretion is much more common at high redshift. You could have different distributions of gas and dust and star formation across the galaxy depending on these different mechanisms. All the local ULERGs that are triggered by major mergers are fairly compact starbursts, so you can understand how the dust is heated to these higher temperatures. Whereas if you have just gas flowing onto a big, large galaxy at a high rate, you can keep the dust fairly cool if it's further away. And different ISM conditions. So there's more gas in general available at redshift 2. We know that. That can lead to higher star formation rates without these dramatic events like mergers. And both of these are also going to affect the relative mass of the black hole. Now the time scales for these are unknown, how you get the gas down there, but they could affect the relative growth of the black hole as well. Okay, so in order to investigate this link between the increased gas content at high redshift and these differences that we're seeing, we tried to link the enhanced PA emission to the molecular gas. Okay, so we started with the sample of sources that we had the mid-infrared spectra, so that we had these measurements of the PA luminosity. And then we went out to find all of the systems in that sample that had CO measurements, which you can use as a proxy for molecular gas. And it turns out there was 10, and then we got a couple of new observations. So here's our massive sample of 12 high redshift galaxies that have both very accurate PA measurements, and very accurate CO measurements. These are all the sources that exist that are unlensed that have both of these measurements. And this will remain the case until JWST gives us more PA measurements. So this is just, this plot here, let me just back up for a second. So before I showed you the PA luminosity versus the total infrared luminosity, and you can see that here I'm plotting the ratio of the PA luminosity to the infrared luminosity as a function of the infrared luminosity. And now I'm plotting some millimeter galaxies in red, but then there's other types of galaxies that have both of these measurements as well. So the blue ones are 70 micron selected galaxies selected on the other side of the dust peak. And then we've got a couple BZK near infrared selected galaxies in here too. So it doesn't really matter. The point is these are where the high redshift galaxies lie. And then if you look at where local galaxies lie, the local ULIRGs that we had before are down here. And then if you extend out to lower luminosity galaxies, you get this big cloud here. Okay? So there aren't very many points here, but it appears as though the high redshift galaxies are shifted on this plot, similar to what you see here, where they're shifted upwards and there may be an extrapolation of the local starburst galaxies. Okay, now when we made this plot, we thought that this looks very similar to what people are seeing with C+. So C+, the 158 carbon line, is the dominant cooling line in galaxies. It's often used as a good star formation rate indicator. Its potential was really realized with Herschel observations for local galaxies, where we got spectra of tons of sources. And with ALMA, we're going to have access to this at very high redshift now. And if you look at the ratio of the C+ luminosity to the total infrared luminosity as a function of the total infrared luminosity, people have seen, even in early time, so just ignore the pink points for a second, that it was fairly flat, and then above a certain infrared luminosity it dropped, and this is called the C+ deficit, and this has been known for 20 or 25 years or 30 years, that the highest infrared luminosity sources have a deficit in the C+ emission. When people started collecting the high redshift observations, these pink ones, they found that they were shifted over. So they did have a deficit eventually, but they got deficient at higher infrared luminosities than the local galaxies. So there was something different going on. And so we sort of saw a parallel between these two things, and knowing that PA emission and C+ emission are both coming from the PDRs, we were trying to make a link here. So
what's a PDR?
Photo dissociation region. So the region between the H2 region and the star formation in the molecular cloud. Sorry, I said I wasn't going to use acronyms, and I just started. So what these people did in this paper that studied the C+, is they then incorporated the molecular gas, and they said, well, I know these sources up here have a lot more molecular gas, so let's normalize this access by the molecular gas. So here's the mass of hydrogen gas, molecular hydrogen gas, as derived from CO measurements. So you measure CO emission, and then you use this magic X factor, and you get your molecular gas. But what you find is that everything falls on a common grid, and you've got this consistent relationship. So we tried this for our high redshift sources. So we had PA emission and CO emission for all these sources. We don't have them for all these local sources, unfortunately, but when you do this experiment and you divide by the CO, they do fall closer to one another. That's all I'll say. There's a lot of scatter. You wouldn't necessarily say that this is a relation, but this has motivated us to try and study this more, and it seems as though the additional molecular gas in these sources is linked to the additional PA emission that we've got in them. This is just the CO luminosity, you'll notice. So I said this magic X factor, I don't want to get into this, but the conversion of CO to molecular hydrogen is very uncertain. It varies by a factor of 10, depending on what type of galaxy you think you're looking at. If you trust the X factors, then this is the plot showing the molecular hydrogen, where the submillimeter galaxies are plotted at a single point because we think we know the X factor. These new measurements that I made at 70 microns, I have no idea what the X factor is, so I just drew the full range so you can appreciate that there. But if you did know the X factor, or that you had a better tracer of the molecular hydrogen, you might say that this observation tightens up, this correlation might tighten up a little bit. Yes?
I don't need to be
No, it's fine.
If you're plotting something over infrared luminosity versus something, and you're always going to get a covariance in that direction. So
right.
You haven't told us what the covariance is.
Right. No, you're absolutely right that as soon as you're plotting the same quantities on multiple axes, you're going to expect correlations. The point that we're looking here is the relative positions of where the local galaxies go relative to the high redshift ones. So that's the difference you're looking at. I'm not going to say anything about the slope of this. I'm just interested in where the colored points are relative to the other points. So yeah, extremely good point. Okay, so it seems as though in this sort of statistically sparse sample, that there's a link between this enhanced PA emission and the increased molecular gas. And that's not surprising at all. That's what we would expect if these things are tracing these PDRs in these high redshift galaxies, these photon dissociation regions, like they do in local galaxies. And so this is something that we can improve on in the future. We need to get more observations of the high redshift sources in molecular gas. We can get more observations of these low redshift sources at these lower luminosities. This is something that I'm really interested in trying to do. And with ALMA, we can start to take higher resolution observations to actually try to map out the gas at higher resolution in the dust. Okay. How am I doing? Five-ish?
Yeah.
Minutes? Yeah, okay.
Okay.
Okay, so I wanted to talk about another sort of important thing. So I've been talking about, we have these galaxies at redshifts 1 to 2. They're undergoing a lot of star formation, a lot of black hole growth. There's a number of factors that can be affecting them. And the environment is something that we know can fuel, trigger, or suppress star formation. And so another sort of parallel project that I've been working on lately is trying to quantify that a little bit more. So we know from the colors of galaxies in the local universe that environment affects star formation. So clusters are made up of red dead galaxies. The star-forming galaxies exist more in groups and in the field. But these clusters must have been actively forming or assembling at some time in the past, and Casey and Bee have worked on this. And so if you look at clusters above redshift 1, I advocate that you should look in the infrared because we've seen that most of the emission is obscured by dust, and so the infrared can provide this additional picture. And in addition, the cluster environment may affect dust-obscured star formation different from unobscured star formation, so it's good to put the two together. So what we did was we worked with this IRAC shallow cluster survey team. So this is a survey of a large 8 square degree field, and what they did was they have photometric redshifts for all of the sources, and they created density maps and selected clusters from photometric over densities. And then they calibrated this method by getting spectroscopy of some large fraction, and they can understand. So they've got samples of clusters in this field ranging from redshifts 0.3 all the way out to 1.5, and some fraction of those are spectroscopically confirmed. For this study, we decided to do a statistical analysis where we just looked at all the clusters and binned them by redshift, and our goal was to measure how the average star formation in the cluster changes as a function of redshift, and compare that to how the average star formation in field galaxies from the exact same field selected in the exact same way evolved as a function of redshift. So this is the average star formation rate that we've derived from the infrared measurements that we've made of these galaxies. This is a mass selected sample. As a function of redshift or age of the universe, we do some stuff with time, which is why we have that on this axis. The blue points here, and see we start at redshift 0.5 because there isn't a lot going on down here, but you can imagine the blue points are what happens in the field. So we know from the previous plots that I showed you that this is the peak period, and so these average star formation rates in galaxies of a given mass have to increase, and we see that for the blue points. The yellow points are just field measurements from another study just to show that we haven't messed up our stacking analysis. And then the black points are the average star formation rates for the galaxies in clusters from this sample. And these clusters are defined as structures that are about 10 to the 14. So you can see at low redshift, they're down quite a lot. If you extrapolate this even further, we know that they're even much further at redshift 0. But already at redshift 0.5, you've got this deficit. But then as you go to higher redshift, the black points ramp up faster, they evolve faster, drawing up to field-like star formation levels somewhere around redshift 1, 1.2, 1.4. This plot at the bottom shows the ratio of these two, the clusters to the field, and so you can see they're below the field level, and then they come up within the error bars to the field levels.
What's the mass limit?
Yeah, I'll double check for you. We did do 2 mass bins at one point, so yeah, I can't remember off the top. I have the paper right on my laptop, so I'll check afterwards for you. Okay, so this I want to advertise. This is my other student, Stacey Alberts, and she just published this paper. And so, so this is just the whole population. I'll refer you to the paper. We actually split these cluster galaxies into 2 mass bins and also into early type and late types to see how much of this rapid evolution is driven by these different populations. So I'll refer you to the paper or talk to you later about those results because I don't have time right now. But what else we did with this full thing is we wanted to quantify this evolution rather than just eyeballing it. So we fit an exponentially declining function with cosmic time so that we could derive some sort of e-folding time scale for the evolution of these 2 populations. We found about 2.5 gigayears for field galaxies over this long, baseline in cosmic time, redshift, and 1.5 gigayears for the cluster galaxies. So significantly higher evolution, a factor of 2 in e-folding time. And we use these timescales in the paper with some arguments and back-of-the-envelope calculations to constrain the mechanisms that are acting to quench the galaxies in these clusters. And we find that things like ram pressure stripping are having a significant impact over this wide redshift range, which is expected. Okay. So we know that environment plays a role in star formation, and we know it plays a role in dust-obscured star formation activity at high redshift. And so one of the things I'm interested in now, I was talking to V right before the talk, is extending this type of analysis to a wider range of environments. Most of the infrared selected galaxies that we've studied in the past, such as submillimeter galaxies, have been blank field submillimeter galaxies, but then if you look around them, they're often in little protoclusters. So there's yet to be a proper statistical analysis of this, so this is something that I'm continuing to work on. Okay, so in the last sort of 2 minutes, everyone's got the proverbial iceberg in their talk and to motivate why they want to keep going. So the ULIRGs, which are the ultraluminous infrared galaxies, are just the tip of the iceberg in terms of the total star formation rate density of the universe. So I showed this plot at the beginning. The total ramps up. The ULIRGs ramp up, but they don't really catch up until about redshift 2.5, and by then you've formed about half the stars in the universe already. It's these LIRGs that are forming stars at 10 solar masses per year that become more important. And these are the sources that are selected as Lyman break galaxies from these UV surveys. So we've selected these galaxies, we know what they are, we've inferred their dust-obscured star formations, but we have yet to directly detect it. So this is an important thing. So we're going to be able to do this in the future. So I mentioned ALMA. This is I should put a proper picture now, because probably all these dishes are almost up there. This is the Atacama Large Millimeter Array, a millimeter array down in Chile at a very, very high site. It's sort of in its commissioning phase as it adds more and more of these antennae, but it's already surpassing all the capabilities from any other telescope in the world. The oversubscription for ALMA, for those who don't know, is similar to HST. It's 10 to 1, so it's extremely competitive. But facilities like this, interferometers, they're really great at getting very, very high resolution, but over a small field. So if you want to study statistics and look at things in a broader sense, you need a big bucket. You need a big single dish. So I'm at the University of Massachusetts in Amherst, and we are co-owners in this large millimeter telescope down in Mexico. Our partner is the country of Mexico. This is a 50-meter diameter telescope. So to put into context, the other submillimeter ground-based telescopes that have been used before are sort of 15 meters. There's a 30-meter in Spain, but for reasons unknown to me, it hasn't really reached its full potential. And the early science instrumentation that we're working with is this camera at 1 millimeter that can survey large regions of the sky at 1 millimeter, and this Redshift search receiver, which is a wide bandwidth heterodyne instrument to basically search for redshifts. So it picks up CO lines. Above redshift 2, you always get 2 CO lines in the band because it's so wide. So you just point your redshift search receiver at your infrared blob that you detect, and you get an unambiguous redshift. Okay, so where are we at with this project? Some of you may have heard of this 10, 15 years ago. It's been fairly delayed due to a lot of political issues collaborating with a country such as Mexico. There's challenges involved. But things are going good now. So in June 2013, we had our first early science run. Now we're only operating with 32.5 meters of the full 50-meter dish. We have yet to, you can see the panels look slightly different here. So these are just dummy panels. We just have the optics illuminating the inner 32.5 meters until we get the funding to get the remaining panels. But even with 32.5 meters, the spatial resolution and sensitivity is considerably more than what we've had before. So here's an example of a high redshift lens submillimeter galaxy. The Aztec image here is just point-in photometry, 10 minutes. We can do it much faster now with the system improved. And this is an example of what these redshift search receiver spectra look like. So this is 1 hour, and you get from 70 all the way to 110. Now in this case, this source is below redshift 2, so you only have a single line. But usually below redshift 2, you have other prior information that can help you sort out of the possible redshift solutions this could be, if it's the 3 to 2 or the 4 to 3. So this is an example of what we're gearing up to do. Ultimately, the goal of this telescope is to do very wide, deep, high-resolution imaging. So this is the sort of the example slide. So here's the Hubble Deep Field. This is 2 arc minutes across. We know that there's all these galaxies at all these redshifts. If we look at this with current sub-millimeter telescopes, this is what we get. So we have a sort of 18 arc-second beam. Here I've even zoomed out to 4 arc minutes, otherwise you wouldn't see anything. So you can see there's like maybe 3 or 4 or 5 or 6 blobs if you really squint. But then determining which counterpart is very challenging, and you can't extract very much information. This is a simulation of these exact same galaxies with the LMT's 5 arc-second beam that we're going to have with the 50 meters. So this is the same as MIPS 24 microns. We're going to be able to match in sensitivity and, well, due to the K correction, our sensitivity as a function of redshift is much, much better. So this is what we're going to have. So we're going to be able to study the dust-obscured activities in galaxies at lower luminosities, the more typical galaxies that are dominating the star formation ring density. We're going to now be able to directly detect in the infrared to be able to study all these processes like I've done with the brighter sample today. Okay, so let me just summarize here. So how is star formation linked to the black hole growth? Can we separate the emission? Yes, the infrared spectrum, particularly the mid-infrared, is extremely powerful diagnostic for this, and if you have very deep far-infrared data, you can extend that analysis. And we observe a difference, a significant difference of 20 Kelvin in the effective dust temperatures between the AGN and the star-forming galaxy. So we're actually seeing direct evidence of the AGN heating the dust within these systems. The other question was, are the mechanisms of triggering and fueling star formation different at high redshift than in the local universe? Sub-question, how do the interstellar medium conditions differ during this period? That we saw very strong PA emission and much colder dust emission in the high redshift galaxies compared to locally. And it seems like these two are linked, but we need to fold in things like the role of environment and increase the statistics considerably to solidify this. So that's what we're going to be able to do with ARMA and large single dish telescopes like LMT and CCAT. Eventually we'll also be able to do this. And that's all.
Thanks, Alex. More questions for Alex? Thanks.
Another question, got a point on LMT. I've been to the LMT site twice. What people don't realize, it's only 2,000 feet lower than the main site. This is a really high site.
It's 15,000 feet.
And it's the highest, to get there, is you go to the highest point you can drive to North America. It's really an amazing site.
So what were you doing down there?
I was advising the Mexican part of the
okay.
operation.
Oh, interesting.
We
Okay.
complained about UMass, so it's interesting.
Well, so I can't really take, I mean, I've only been at UMass for 3 years, and I have colleagues who arrived in 2000 and were told this telescope would be available in 2 years, and we are now, you know, but these things happen, delays happen, and yeah.
And to be honest, it really wasn't UMass. So it wasn't University of Massachusetts, it was Mexico, but they wanted something else.
Yeah, okay.
Absolutely.
Yeah, so yeah, I didn't emphasize that. So this is sort of 2 hours from Mexico City on a mountain at 15,000 feet, so higher than Mauna Kea in Hawaii. And unfortunately, the base camp is quite a bit, it's about an hour drive from the summit. So when you go up for your 14-hour shift, then you have an hour drive to get down to HP-like levels of 9,000 feet to sleep. So yeah, I actually haven't been yet. I was supposed to go, and then I got pregnant and had a baby, and you can't go to 15,000 feet when you're pregnant, so that was my excuse, but.
Yeah, Lisa.
So these units, they are powerful supernova producers. They
Yes.
produce like a few supernova each year, and those are, you know, kinematically, you know, that can heat up the dust or it can form dust by themselves.
Yep.
You know, those supernovas. So and are those, you know, important contributors to the infrared or, you know, these things?
Yeah, so that's a really good question. Where do I start with that? so the buildup of dust in general in the universe is, you know, an interesting question, right? How much is produced by AGV stars? How much is produced by supernova? At the very highest redshifts, we think it has to be the supernova because the time scales aren't long enough for the AGV stars. So there have been a number of detailed studies that have tried to look at the sub-millimeter galaxies that we see up at redshifts 4 and 5 and quantify their dust masses and put constraints on which processes could act. I think the highest redshifts that we're seeing these systems now still aren't high enough to say definitively this fraction of the dust must have been made by supernova as opposed to AGV stars. But I think that's an area people are trying to push this to higher redshift. There was a Nature paper earlier this year that found one of these systems at redshift 6.3. So there you're starting to get in the region. There's issues to do with lensing, so it's hard to know. So in terms of producing dust, I'd say it's something interesting that people want to pursue more with larger samples, for sure. You were also asking how much it could contribute to the infrared luminosity?
because all this kinematic energy will end up in somewhere in the infrared.
Yeah.
So most of those will be released in the infrared.
Yeah.
Yeah, and it's producing each year. Signal one can produce maybe a few solar mass of dust.
Right. Okay.
And with if you add up maybe 50 or 100 years, they're going to be clear.
Yeah.
They're all going to be meeting.
Yeah.
It's a huge amount of dust.
Yeah. Yeah.
Producing.
Yeah. So I haven't seen I haven't seen any studies that have looked in detail at this. I mean, my gut feeling is that because the star formation rates are so, because you have such a strong baseline to start with, I would think that they wouldn't be contributing a lot, but I'm not an expert in sort of the supernova rates and these types of systems. I guess it depends, right, it depends on the star formation histories and all these things of the galaxies as well, but. Yeah. The main thing with supernova is like the early dust production mechanisms, and that's sort of one of the drivers for, ALMA wants to detect dust at redshift of 6, 7 in some of these systems so that it can put constraints on that. And then the other thing is feedback, right? So starburst winds and stuff like that is a big thing that people are trying to study in these galaxies when they see this sort of you can see signatures for, these systems unfortunately aren't the same ones that you're able to see outflow signatures in optical spectra because they're almost invisible in the optical, right? But you can look for outflow signatures even in the CO lines, and in local ULERs people have seen that they're brought in, and so then if you can determine if they're AGN dominated or starburst, you could maybe then say that you're getting winds from the supernova from that. But yeah, no, that's an interesting question. I'm actually not sure.
Right. So you showed that the dust temperature decreases from low redshift to high redshift at some given star formation, right?
Yeah.
And okay, so to get Euler-like luminosities at low redshift, you sort of need a merger.
Yeah.
At high redshift, that wasn't necessarily true. It just a typical massive star-forming galaxy could be Euler. So can we say if this is somehow the decrease in temperature is due to the merger?
Right, yeah, so this is, so I didn't sort of delve into that too much because I never know based on the crowd how much of the merger versus cold flows thing to get into, and then actually lately I kind of ignore it. But yeah, exactly. The fact that you're seeing more cold dust surviving is an indication that the dust is more distributed in these systems, which, maybe mergers at redshift 2 because the universe is different and it's more gas rich, the mergers can be more spread out, but it would be more consistent with a scenario where you have just sort of a disk galaxy, clumpy disk galaxy fed by cold flows. And in fact, some observations are being made now at high resolution of the molecular gas. So Rob Iveson has some papers from UVLA where he's measured enormous sizes for the molecular gas reservoirs for these systems, and the dust would trace the similar size. And so in those systems, they look like massive rotating disks, and that they're not mergers. And those are the ones that have the cooler dust temperatures. So there definitely is a link there. If you talk to someone like Deshika Narayanan or Chris Hayward, they'll tell you that they can have, cooler dust temperatures at different stages of their mergers, and so you have to fold all that in. So
okay, so I'm not familiar with this work by Iveson, but you're saying at a given redshift, you can look at galaxies that look like they're mergers and galaxies that don't look like mergers, and you do see a difference in dust temperature. That's not the word. So so yeah, let me just back up. So the Iveson work is taking submillimeter galaxies, so things that we maybe thought would be major mergers, and mapping out at high resolution the molecular gas, and you can see that they're disks and that they have very extended reservoirs, which can explain their colder dust. So when we found the colder dust, right away we said the dust is more extended. Probably they're not major mergers, but you don't have any evidence for that. It's just like inferring. So now Rob's actually measured high resolution observations and shown that you do have these extended reservoirs of gas. Yeah, they're huge. So, but what you said is actually something that I've been trying to work on, is take samples of galaxies that are mergers and are not mergers, and then measure their average dust. And so that's something that I've been trying to get a student on. I was telling Keith I don't have enough money for enough students, but you could do this in candles, right? You could select galaxies that are clear. Because the thing is, when you're looking at an individual galaxy in candles, you can say, ooh, clumpy disk, major merger, I don't know. But if you just look at the ones that like this is definitely a major merger, everyone agrees, and this is definitely a disk, and then go and look at the properties of those, that's probably a better way to do this experiment. So, yeah. What redshift do you need to go to do that? Do you know?
Redshift 2 is kind of the right area, but you could probably do it at Redshift 1 as well.
Right, somewhere where can have ULERs that are not major mergers.
Right, exactly. I mean, the ULERs, you see where how the ULERs are ramping up in that plot. You just don't have as many of them until you get to higher redshifts. But you do have them between, once you get above redshift 1.
Yeah, I mean, I would think that you could do this. Candles obviously would be great, but you could do this using bigger fields, Cosmos. Because you have the HST imaging, and if you can go out to redshift 1 to get enough, quiescent disk-like ULERs, then the...
Yeah, I think there'd be less of the mergers, right? If I'm remembering, Jehan Kartaltepe did sort of the merger analysis in Cosmos, and it seemed like she didn't have that many. Yeah. And when you're going to the low, you also have the deep infrared data too.
Well, this is why I'm saying Cosmos, because that has sort of the deepest, at least from Herschel, it has the deepest imaging.
No, you could do it over Cosmos as well. I was thinking candles because that just seemed more obvious.
Alex is around the rest of the day. We scheduled grad student harassment. I moved it up by 15 minutes. I think it's 3:30 now.
Am I getting harassed or are they getting harassed?
We don't know which way the back and forth is. It's up to you and to decide. But otherwise, you can ask me. I'll know where she is if you find her. But let's thank Alex again.